Okay, in this video, we are going to start to look at some of the math pieces that are going to come in the equilibrium unit. So basically, I'm going to introduce you to the equilibrium constant, how we write it, how we calculate it, and what the numbers that we get out of it mean. So you are going to find when we are talking about the equilibrium constant, the symbol that is generally used is Kc. Okay, but if you start looking online, you might find some things that say KEQ. It's just an older notation, isn't really used anymore, but is definitely still around there. So when we are calculating an equilibrium constant, we always need to look at our equation, the way it's written, and how it's always going to work is that Kc is going to always equal the concentration of the products to the power of whatever coefficient we balance with, divided by the concentration of the reactants to whatever power we balanced those with. So things to watch out for is because these are concentrations, we only want to include aqueous and gas. So that means the liquids and solids do not belong inside of a Kc expression. So if I wanted to write a Kc for this equation here, right, and this is kind of a generic equation, we would say that Kc equals, okay, and then we're going to start with the concentration of the products. So the first products we have is C, and that is going to be to the power of whatever the little c we balanced with is. And then that's going to be times the concentration of D to the power of whatever D we balanced with, okay, and all of that is going to be divided by the concentration of our reactant. So we are going to get the concentration of A to the power of the A that we balanced with, to that bit more, and then times the concentration of B to whatever B we balanced with. Okay, so it's always going to be the products on top, the reactants on the bottom, concentrations, and then to the power of whatever we balanced with. Again, only aqueous and gas get to go into this. If there's a solid or a liquid, it will not get placed into this. So Kc is always going to be for the forward direction because it's the products over the reactants. And if we were dealing with the reverse direction, we would have to flip that whole thing over. So you do find, though, that because of that, the Kc of the forward and the reverse are just the inverse of each other. So it's pretty straightforward to be able to determine what it is. So when you think about these Kc values, they do tell you something. So when we actually plug some numbers in and get an answer for K, we kind of have three options. Generally, those options are going to be that Kc is less than 1. That's the right symbol. Hold on. I'm having great issues here. It's less. Oh my goodness. There we go, is less than 1. We're going to have that Kc is approximately equal to 1, or we are going to have that Kc is greater than 1. Okay, so those are kind of our three options. So if we think about the general setup of Kc, and that Kc is going to equal our products over our reactants, these possibilities of greater than 1, less than 1, or approximately equal to 1 are going to give us an indication of where that equilibrium position lies, right? So the simplest one is a Kc approximately equal to 1. For me to get that Kc is approximately equal to 1, that means products and reactants have to be approximately equal to each other, which means my equilibrium position lies near the middle, because when we lie near the middle, the amounts we have of both are going to be about the same. In the case of Kc being less than 1, for it to be less than 1, we must have a lot of reactants compared to products, right? This number must be really big, and this number must be much smaller to get something less than 1. So when Kc is less than 1, that means that reactants are going to be favored. And then on the other hand, if we find that Kc is greater than 1, that must mean we have more products than we do reactants. Therefore, products are favored. So the numerical value of K gives you an indication of where that equilibrium position lies, and what is being favored. Okay, so big K, we are favoring products. K close to 1, it lies near the middle. A really tiny K, we are favoring reactants. Okay. So solids and liquids, I already mentioned, they do not belong in KC, and that is because their concentrations don't change. Their concentration is dependent on their density, so we are not going to include them. We are only going to put aqueous and gas into this. You're going to find on the diploma, they're almost always going to throw a question at you that involves water, and one of the options is going to be the right KC, obviously, and one of them is going to be the right KC, but also with that water thrown in, which therefore makes it wrong because we can't throw a liquid into our KC expressions. So the numerical value of K. You are going to see that when we talk about the numerical value of K, we call it an equilibrium constant. A constant means it doesn't change. There is one exception to that. You're going to find in Chem 30 we have a million exceptions to the rule. You are going to find that temperature is the only factor that has the ability to change Kc. So I change pressure, doesn't change Kc. I change concentration, doesn't change Kc. I change volume, doesn't change Kc. But I change temperature, and that is going to impact Kc. Okay, what you're going to find is you basically have to figure out which way the equilibrium position is going to shift. If it's going to shift towards reactants based off of the temperature change, because Kc is set up as products over reactants, if we're going to increase the amount of reactants, we are going to decrease the value of K. If it shifts towards the products, we're going to have more products on top, less reactants, and it is going to decrease the value of K. So you have to be able to look at these questions, determine the direction of shift for that temperature change, and then based off of that, you can determine the change to K. Again, only for temperature. Don't start doing this for other things because they don't actually change. Okay, so let's look at some examples of writing some KCs. So first equation we have is N2 gas plus 3H2 gas to give us 2NH3. So we're going to have that our Kc is equal to, so we're going to put our products, so concentration of NH3, and because it was balanced with a 2, that is going to be squared. Okay, then that is going to be over the concentration of the reactants. So concentration of N2, that doesn't go to the power of anything because it was balanced with a 1. Okay, and then that's going to be times the concentration of H2, which we are going to cube, and we're going to cube it because it was balanced with a 3 in our equation. So for that one, we get that Kc equals the concentration of ammonia squared divided by the concentration of nitrogen and the concentration of hydrogen cubed. Okay, let's look at the next one. So we have AgCl turning into Ag plus Cl minus. So Kc equals, so we're going to do, it's not concentration of that Ag plus. Okay, it's not going to be squared or cubed, it's balanced with 1, so we just leave it, then times the concentration of that chloride ion. Okay, and then we're going to put this over nothing. So why are we putting this over nothing? We'll have a look at this. This is a solid. We said solids don't belong in Kc. So either I can put this over nothing, or if I really want, I could put this over 1. That would be the same thing. Okay, but I do not get to put the concentration of AgCl into my Kc expression because it's not aqueous or gas, it is a solid, and solids do not belong. Okay, so looking at the next one, we have calcium carbonate turning into calcium oxide and carbon dioxide. So this one, we're going to have that Kc equals. So CaO does not belong. It's a solid. It doesn't go into it. So we move to the next thing. So we're going to have the concentration of CO2, not to the power of anything because it's balanced with 1. And then we go look at our reactants. The only reactant we have is calcium carbonate, which is solid, so it also doesn't belong. So in this case, our Kc is simply equal to the concentration of the CO2 gas. Okay, the last one on this page, we are going to have that Kc is equal to the concentration of that copper 2 ion Okay, again, not to the power of anything because it's balanced with a 1 times the concentration of ammonia. And this is going to be to the power of 4 because it was balanced with a 4. Okay, we go to our reactants. It's aqueous, so that does get to go into my K expression. So we're going to have the concentration of that copper ammonia, or wait, the 4, hold on, a whole lot of subscripts going on here, and superscripts. There we go. Okay, so that one is going to look like that. So most important piece, products on top, reactants on the bottom. Make sure you are checking your states, because if you're not checking your states, you're going to wind up putting something in your Kc expression that doesn't belong in your Kc expression. So I don't want to say don't fall for that, but don't fall for that, right? You need to make sure that you are aware that those things do not belong. Okay, so here's another example. So it talks about the contact process. You're going to see we're going to talk more about this when we get into applications of equilibrium. So we have 2SO2 plus O2 to give us 2SO3. So it's asking us to write the Kc expression. So we're going to have Kc equals. So we're going to have concentration of the products. So the SO3, and that is going to be squared. Same thing, there we go. And it's squared because it's balanced with a 2. And that is going to be divided by the concentration of SO2, which is going to be squared because it was balanced with a 2, times the concentration of that oxygen. Okay, so there is our Kc expression. So part B, explain why industrial plants operate at a pressure of around 200 kilopascals. So if you remember back to last year, we talked about how room pressure or general pressure is usually just above 100. So that means this is operating at a higher pressure than normal. So why might this reaction want to operate at a high pressure? Well, remember when we talked about pressure, we talked about gas molecules. If I look at this, there's 3 on this side and 2 on this side. So if we operate at a high pressure, that means that we just increase the pressure. Our system is going to want to do the opposite, which is going to be to decrease the pressure. The way it's going to decrease the pressure is going to be to favor the side with less molecules, which just so happens to be the products, which is what we're actually trying to make. Okay, so that's why it's going to operate at high pressure, because Le Chatelier's tells us that a high pressure is going to favor the side with less molecules, which in this case also so happens to be our products. Okay, here you have another example. So write an expression for Kc. So if we look at this one, we are going to have that Kc is equal to the concentration of hydrogen times the concentration of carbon dioxide. And that is all going to be over the concentration of our reactants. So the concentration of water and the concentration of carbon monoxide. Okay, nothing gets any squares or cubed because everything balanced with a 1. Okay, so B, would you expect the numerical value of Kc to increase, decrease, or remain unchanged if the temperature were increased? Explain. So it's a temperature change. We know Kc is going to change. If it wasn't a temperature change, I would be choosing remain unchanged. So if we look at it, it says that we increased the temperature, right? The temperature was increased. So if we increase the temperature, that's what we did. The system wants to do the opposite, which is going to be to decrease the temperature. The way it's going to decrease the temperature is going to be to go in the endothermic direction, right? Because endothermic feels cold. So we know that it's going to go in the endothermic. So we need to decide which way is actually endothermic. So if we look here, the energy term is over on the product side. If you remember back to when we did Le Chatelier's, we said that when the energy was on the product side, that told us that the forward direction was exo, which means by default, the reverse has to be endo. So we've already decided that this system has to go in the endothermic direction. So we know that it's going to shift this way. So that means the concentration of water and carbon monoxide is going to increase, and the concentration of hydrogen and carbon dioxide is going to decrease. Okay, so if I make the number on the top smaller and the number on the bottom bigger, overall, the numerical value, not increase, why am I doing that? Sorry, is going to decrease. Okay, so kind of comes down to mathematical reasoning when we are talking about what's going to happen to Kc when we do these temperature changes. However, you obviously have to also be able to apply the Le Chatelier's concept to the question as well. Okay, so the relationship between Kc of the forward and Kc of the reverse. I kind of talked about this in the very first slide of this lesson, right? If you think about it, when we write a reaction, right, and I'll write it pretty simple here, just to make life easier. We generally say that reactants are on that side and products are on this side, and I'll throw an arrow in here. Right, so if we were looking at the Kc for the forward, which is what we always write the Kc of the forward, right? That's always going to equal the concentration of those products over the concentration of those reactants. Okay, but if instead of doing Kc of the forward, we were dealing with Kc of the reverse, okay, what changes is technically if I was dealing with the reverse, I wouldn't have written it as products turning into, or reactants turning into products. I would have written it as products turning into reactants, right? Because that's the reverse. So if we look at it this way, if I were to write out this Kc expression, I come up with the concentration of the reactants divided by the concentration of those products. So if you look at these, the relationship between the forward and the reverse is that we flipped the products and the reactants around. So what that means is they are the inverse of each other. So if I know what the Kc of the forward is, I just have to do the inverse of that to be able to determine what the Kc of the reverse reaction is. It's a pretty straightforward thing. You definitely will see questions on that on both the diploma and unit tests, so please make sure that you are prepared for a question like that. Sometimes because we don't spend a lot of time on it, you guys kind of just skip it and you think it's not really important, but there are definitely some small concepts that do show up pretty often. Okay, so let's look at actually throwing some numbers into our Kc besides just talking about how to write them, because writing them is really just a precursor to the actual calculation pieces. So we get some simple Kc calculations like this one here. So we've been given our equation of 2SO2 plus O2 to give us 2SO3. Okay, any question, even if it's a calculation question, you still need to make sure that you are writing out what your equilibrium constant expression is. Couple of reasons. One, if it's written, we give you marks for it. Two, and probably the more important reason, when you guys don't actually write it and you jump right into throwing numbers in, you tend to lose your squares and your cubes and things like that, and then obviously you get a totally different number at the end. So really important to please make sure that you do actually write out your equilibrium law expression before you plug numbers in. So we're going to get our SO3 squared because that is our only product, and that is going to be divided by SO2 squared times that O2. Okay, so step one looks the same as what we've been doing in the last couple examples. Now what changes is we are just going to actually throw numbers into this. So this is going to equal that 0.8 squared, and that is going to be divided by 1.2 squared times 1.0. Oops, sorry. Okay, you're going to notice I didn't put any units in. The reason I didn't put any units in is generally when we talk about Kc, we don't include units. And it's not because it doesn't have units, it's because every single Kc has the potential to have different units. So there's not really a need to write them, okay? But we do know they are concentrations, so we do know that they have units of moles per liter. So, you're going to do 0.8 squared divided by 1.2 squared divided by 1. So sig dig wise, we get to have 1 because 0.8 only had 1. So we get us an answer 0.4. Okay, so super simple KC calculation. You're literally just plugging equilibrium concentrations into it. Okay, really important to recognize when you are doing KC calculations, it is an equilibrium constant, so it must be equilibrium concentrations going into it. If they give you initial concentrations, those do not belong in your KC calculations because they don't represent equilibrium concentrations. And you will find that in the next lesson, we are going to talk about how you approach questions like that don't give you equilibrium or only give you some equilibrium. So at this stage, most important piece to get out of today is how to write a KC expression, to recognize that solids and liquids do not belong in it, and to recognize the relationship between the KC of the forward and the KC of the reverse.